how does GSE fit into our system? Let me describe it. I'll start with the most basic diagram you've ever seen, and you've seen it many times before, I'm sure. Here's a satellite. Here's a transmitting station. It's going to transmit up to the satellite, and somewhere out there, there's a receiving station. That's going to receive from the satellite. Now, in reality, there are multiple transmitting stations, and probably multiple receiving stations as well. That doesn't concern us for the moment. And these transmitting stations will have different data streams of different types. Some may be broadband, maybe even video. Some may be extremely narrow band. And receiving stations also come in different flavors. They may be small stations that are only capable of receiving narrow bandwidth signals, or they may be large stations and capable of receiving anything the satellite can transmit. And we want to accommodate all this at the same time. And adaptive coding and modulation is the fundamental trick for that. We want to be able to transmit some data with very high coding, with every possible advantage for a small receiver, at the cost of some bandwidth, and other data we have to transmit with less coding, but we can send more bits. So with all these multiple streams coming up at the satellite is going to have to assign a receiver to each incoming stream. Of course, the receiver is a bit of software or some FPGA resources. It's not a physical receiver necessarily. And each one of these streams will go into some receiver and come out as a data stream. So there's a buffer here with some data. And then these have to be all combined into a single stream that will be transmitted on the downlink. And using the adaptive coding and modulation, of course. And the way to do that we've chosen, the DVB-S2 way to do it, is called GSE, or Generic Stream Encapsulation. And in this case, there will be some module here, which we might as well call the GSE module, which takes in these multiple data streams and generates a single data stream out, containing all the different adaptive coding and modulation decisions that have been made. And then there will be, of course, a transmitter, which has the capability to modulate all those different schemes and will transmit the signal data stream. So all of these have to go in, be combined according to some policy based on priorities, which things are real time, which things are not real time, and combined into the single stream and then transmitted. So this is how the real system will work. We can't build all this all at once and test it in one giant system, so we have to break it up into pieces. And right now Ron is concentrating on this piece here, the GSE transmit side. So what does his simulation environment look like? Let's take a look at that next. So Ron's simulation environment for GSE development. He's got GSE implemented inside of GNU Radio. So the basic picture is, here's a computer running GNU Radio. And it is going to transmit through an SDR, such as an EDIS USRP. And then actual RF comes out here. So this simulates, in a sense, the entire set of transmitting ground stations and the receivers at the satellite and the multiplexing system and the modulator and the transmitter. So a downlink signal is coming out here just like it would from a real satellite. And then to simulate the channel, all we need here is an attenuator, which I'll draw like a resistor, but it just reduces the signal strength is all. And then we need some kind of actual receiver. And we've been able to obtain a commercial receiver called an SR1. And Ron is testing against that as a baseline. So he runs the signal directly into the SR1. SR1. And it understands GSE, and it understands adaptive coding and modulation, and it generates an output as if it were a satellite receiver. And this output comes over an Ethernet. And it strips off all the GSE stuff, in fact all the DVB-S2 stuff, and all we have here is the payload data. So let's look inside this GNU Radio block a little more carefully. In fact, we're going to have to make this block bigger so we can make more annotations inside it. So there's, of course, a transmitter that does all the modulation and stuff. We won't talk about that very much right now. But inside this, there's the GSE block, just like we had in the real diagram. And it's generating a data stream for the transmitter. Coming into the GSE block, we've got some kind of traffic generator. It could be anything. It could be generating a simulated voice stream or simulated video stream or a simulated data stream of some kind. The easiest thing to do is generate a simulated data stream and using TCP/IP. So for Ron's tests, he's either been generating a series of pings, which is a UDP carried format using ICMP, or just a series of raw UDP packets with some random data in them. But these packets come out here, and they go into his GSE module, which he's written to be combined into a generic stream. So what we need to do to test this is to look at this data to make sure that we've generated what we think we generated. And then all the way over on the other side, where it comes out of the SR1, we need to see that we have the right stuff coming out. So whatever we put in here from the traffic generator should be coming out here at the receiver. So there's an Ethernet bus. He uses just one. And he's got the SR1 connected to it, and he's got a way to take these packets coming out of the GSE module and feed them out to the bus as well. Meanwhile, we're able to capture what goes on this bus and inspect it later. So by generating some random traffic and encapsulating it with GSE and then transmitting it through the SDR, receiving it with an actual commercial receiver that is known to have GSE support, and then taking a look at the output, we should be able to do an end-to-end check of the entire flow, including particularly the GSE encoding that Ron is working on. Ron has been mentioning some of these little elements of progress on Slack, and he happened to mention that he was using a tool called Wireshark to look at the packet data that he had generated. Wireshark is familiar to many of us who have worked on computer networking before. It takes a raw capture of packets, which it can take itself off the Ethernet wire, and inspects it. So it pulls it all apart. Every single packet gets reduced to its individual fields so you can inspect it and see that it's right. And Ron happened to mention that there were some bugs in the Wireshark module for DVB-S2. That caught my eye, and I dug in and learned how to be a Wireshark developer, or at least I'm on the way to learning how to be a Wireshark developer. And I've been making some changes to what they call the dissector, the piece of Wireshark that pulls apart a packet for DVB-S2. So I've taken captures from Ron's test setup from this Ethernet wire, which he has courteously provided to me, and looked at the individual test cases that he was worrying about. And in some cases I found bugs in his implementation, but mostly I found bugs in Wireshark, and I was able to fix some of them and add some enhancements to the dissector for Wireshark. So making a little contribution back to the open source community through Wireshark. So if you want to learn more about what Ron has been up to, you can follow his code commits on GitHub. This URL, https github.com, Dr. MPEG, that's Ron, GR-DVB-GSE, GNU Radio, Digital Video Broadcasting, Generic Stream Encapsulation. My contributions to Wireshark are not yet in the mainstream, although I'll be checking them in over the next week or two. But you can get Wireshark from here. It has an older version of GSE capabilities in it, and we'll soon have my improvements.